Stanford University.
Let's spend a few minutes talking about units. In particular, the Boltzmann constant. What is the Boltzmann constant? The Boltzmann constant, like most or like many constants in physics, are conversion factors. The speed of light is a conversion factor, you know that, and the conversion factor from distances to times. And of course, if you judiciously choose your units, you can set the speed of light equal to 1. The Boltzmann factor, the Boltzmann constant, is also a conversion factor. And typically these things are conversion factors from what I tend to call human units to units which are in some sense more fundamental. Human units are units which are convenient for scales and magnitudes of quantities which people can access reasonably easily. Okay, so we haven't talked about temperature. We're going to talk about temperature, but I thought I would just say something about units first. The units of temperature as invented by, I guess, 19th century physicists and chemists. I'm not sure when Fahrenheit was. I know Kelvin, of course, was late 19th century. I'm not sure who or what Fahrenheit was. 17th century. Fahrenheit was 17th century? So very early. Wow, okay. But in any case, the units that we tend to use these days are Kelvin units or centigrade. It's the same kind of unit. Kelvin, temperatures Kelvin are relative to absolute zero. Temperatures centigrade are relative to what, the freezing point of water, which is a totally arbitrary thing. And the centigrade scale, the unit of 1 degree, as you well know, was simply set by the arbitrary choice to divide the temperature scale between freezing and boiling of water, freezing and boiling of water at atmospheric pressure, into 100 units. Highly arbitrary. Didn't have to be water. I mean, it was water that was used. If we would have used alcohol, it would have been a different unit. If we would have used, and so forth and so on. But it was a unit which people could manipulate. People could manipulate temperatures. They could measure temperatures. It's not too hard to measure a change in temperature of a degree with a human scale thermometer. By human scale, I mean, you know, it's made out of a lot of atoms. It's a thing that you can make in your shop. And so the degree Kelvin, the 1 unit degree of temperature change, is a human construct that was invented for convenience, if you like. Now, it was, at the time, it was not fully understood, although Kelvin may have understood it, but it was not fully understood that the natural units, the real physical units that temperature has to do with is energy, that a temperature is really an energy. For example, an example is that the temperature of a gas, for example, determines the kinetic energy of the molecules. And one measure of the temperature of the gas is just the kinetic energy of the molecules. Well, you might say, wait a minute, that's not so good, because if the gas is a composite of helium and oxygen, I don't know if it's a composite of helium, and I choose helium because I don't want it to explode, but helium and oxygen, then do I mean the helium atoms or the oxygen atoms? Surely they have different kinetic energy, but they don't. In thermal equilibrium at a fixed temperature, we will prove this. Eventually we will prove this. All of the atoms have basically the same kinetic energy. And in fact, if you put a bowling ball, suspended a bowling ball at finite temperature into a gas or even a liquid, the kinetic energy of the bowling ball would be exactly the same as the kinetic energy of an oxygen atom. Now that seems a little bit odd, but when you think about it, it's not that odd. If the bowling ball has the same energy as a single molecule, it will surely move a lot slower than a single molecule, for the reason is that its mass is much larger. So if mv squared for the bowling ball is the same as mv squared for the oxygen molecule, the bowling ball will be moving a lot slower. But the main point is that temperature is really a measure of an amount of energy. So the natural units for temperature are really energy. But at the time that temperature first started to be measured, nobody could measure a molecule. Nobody had the vaguest idea how big molecules, how massive molecules were, how much energy a typical molecule had at a given temperature. In fact, probably in the beginning, nobody had the idea that temperature had to do anything to do with the energy of a basic constituent. So the scale of temperatures was defined before there was a notion that temperature, so to speak, equals energy. Okay, so the natural unit for temperature could be joules, for example. A joule is a good unit of temperature. It's a rather large unit of temperature. To see that, the typical energy of a single molecule in thermal equilibrium at a temperature of room temperature for one molecule is a tiny, tiny, tiny number in joules. And so the conversion factor between human units and, let's say, the basic units of energy is going to be a very large or a very small number, So let's just define it. I can define it by giving you the relationship between the energy of a molecule in a dilute gas, energy of a single molecule in a dilute gas, dilute because we don't want to worry too much about the energies of interaction between the molecules, and the energy of kinetic energy. The kinetic energy of a molecule in a dilute gas is equal to 3/2. Now, the 3 is easy to understand. What does it have to do with? The dimension of space, number, right. It has a kinetic energy for moving along the x-axis, it has a kinetic energy for moving along the y-axis, and it has a kinetic energy for moving along the z-axis, so there's a factor of 3. And the half, well, that's just a glitch of definition. All right, so 3/2, the Boltzmann constant times the temperature, but this is the human scale of temperature, so it could be Kelvin. Temperature measured in Kelvin units. In that case, the Boltzmann constant here has units of energy divided by degrees Kelvin. Energy divided by degrees Kelvin, and it's a rather small number, as you might expect. If the temperature is 300 degrees, that's room temperature. Temperature Kelvin is 300 room temperature. The energy of a single molecule is clearly very, very, very small, and so 300 is pretty big. E is terribly small. K Boltzmann is very small, and this number in human units now means standard units, meters and so forth. K Boltzmann is about 1.4 times 10 to the minus 23rd. It's no accident that Avogadro's number is also roughly 10 to the 23rd. Not an accident, but and the units are joules divided by degrees Kelvin. The unit of a joule is a unit of energy, and so it's a unit of mass times a velocity squared. We could reduce it to the standard units, get rid of the joules if we like, but this is what it is. Main point is that the really interesting quantity here, temperature in fundamental physics always comes in multiplying K Boltzmann. It's in all fundamental formulas of physics. K Boltzmann times temperature comes in, and that's just because the fundamental quantity is really energy. And so we redefine K Boltzmann times temperature has units of energy. We redefine a new unit of temperature, let's call it capital T, which is just K Boltzmann times the human unit of temperature. And once we do that, we will get rid of degrees, we will get rid of K Boltzmann in all equations. We'll never see it again. But you do have to remember that what I call temperature differs from thermometer temperature by a very small factor. Okay, that same factor actually is there in units of entropy. Remember what entropy is? It's a unit of information. It's measured in bits. It's measured in fundamental little bits of information. At the time that entropy was discovered as an interesting quantity which always increases, it was discovered by a steam engineer by the name of Carnot. And he was a steam engineer. That's what he did for a living. He designed steam engines. He didn't know anything about the microscopic underlying principle of entropy. He had a quantity. The quantity wasn't so easily measured, but he had a quantity defined in terms of temperatures and energies and so forth. And he called it entropy, or somebody called it entropy. And it got the letter S. And I'm going to call it little s for a minute. And I'm going to put a sub-Carnot here. So Sadi Carnot had a quantity which he called entropy. It has units. Let's see, what are its units? Let me cheat over here for a minute. It's energy divided by temperature, but if temperature measured in Kelvin, then it's joules per Kelvin. All right? Joules per Kelvin was Carnot's unit of entropy. But in modern physics, we think of entropy as being measured in bits. A fundamental unit of entropy is logarithm of 2, for example. And that's dimensionless. So there's some other notion of, it's not another notion, it's just a conversion factor again. Carnot's unit of entropy differs by what I have called entropy up till now. I have to get the, yeah, okay. Do you remember what entropy is from a statistical point of view? If you have a probability distribution, if you have some probability distribution over some discrete set of states, then we define the entropy S, capital S now, to be minus the sum over all the states of p sub I logarithm of p sub I. We did that last week, and it's a rough measure of the logarithm of the number of states which are important under a statistical distribution here. That's what we called entropy. What's the connection between Carnot's entropy and this is Boltzmann's entropy? Boltzmann's entropy here, what's the connection? The connection is simply a factor of K Boltzmann, and it is such that this is equal to 1 over K Boltzmann times Carnot's quantity. In other words, when Carnot's entropy is a normal number like 6 in a steam engine, Boltzmann's entropy is enormous. Boltzmann's entropy is roughly proportional to the number of molecules in the system, or something like that. But once we know this now, once we know how to go back and forth between human units of temperature and human units of entropy, And the more fundamental units, for temperature, it's energy. For entropy, it's a dimensionless quantity. Then from now on, I will not introduce K Boltzmann. The Boltzmann factor effectively is gone out of all of our equations, but you can put it back, and the way of putting it back is always, whenever you see capital T, and you want to get it into human units, think of it as K Boltzmann times temperature in Kelvin. And whenever you see an entropy S, which has a huge, huge value typically, and you want to get it into steam engine units, divide it by K Boltzmann.
Question?
Yes.
So your new units for temperature called capital T,
Yeah.
Other than that factor 3/2, isn't it just joules?
It depends on, of course, now it depends on what unit of energy you're using. So if you're using the energy unit joules, then it will be joules. And the point is, it's not a new unit. What is a joule? A joule is the energy in MKS units, MKS meters, kilograms, seconds units. So what is it? It's the energy of a 1 kilogram object moving at a velocity of 1 meter per second. I think there's a factor of 2, 1/2 mv squared in there, so it's twice the energy of a 1 kilo object moving at 1 meter per second.
But as you have that written up there,
Yeah.
you got very specific that the temperature is in Kelvin. That's a very well specified thing. You have a very definite constant there.
No, no, it's not a very definite constant. If you change units, K Boltzmann will change. If you change units, instead of using Kelvin units, we use Fahrenheit units, then K Boltzmann will change.
Right, but I'm just looking at your equations up there, and you got the temperature in Kelvin. And so
Yeah, I was doing that as an illustration.
Okay, got it.
Right, that's right. Right. All right. So energy itself is a quantity with units, and so you have to specify what units you're talking about. When I say temperature has units of energy, yes, it does, but you have to pick your units of energy. So if you're working in the meter, kilogram, second set of units, then your natural unit or your unit of energy is called a joule, but it's not a new unit. It's the unit of energy in MKS units, and that's the unit that you would use for temperature if you want to keep your formula simple. On the other hand, you could use I don't know, kilotons of TNT. Oh, that's a bad thing to talk about today. Some other unit, electron volts or Planck masses or whatever. You change your units of temperature. You change your units of energy. The temperature will also change, but your units of temperature and energy should be kept the same. Entropy, on the other hand, is dimensionless. This entropy is dimensionless and doesn't have units. Yeah.
another question. Is the constant itself, is that essentially determined experimentally?
Yes. Yes. Boltzmann himself, like Newton, never knew the value of his own constant. I don't mean the usefulness, I mean the actual numerical value. And that's because nobody had measured the properties of atoms, the masses of atoms at all, until Einstein came along and figured out how to do it. So Kelvin died just before the value of his constant was really. I'm quite sure that they had a rough idea. And he certainly knew that it was connected to Avogadro's number. But he probably never knew with any detail what the value of his number was. The same was true of Newton. Newton had a rough idea of what his constant was, but no precision. Okay, so, but Boltzmann did understand. He did understand that if only he could measure the properties of atoms, that energy would be related to temperature through his constant. That he did understand. Okay. All right, but thus far, I have not told you what temperature is. You have an intuitive sense of temperature. That's because when you touch a hot thing, it does something to your nerve cells and so forth and so on. And you have a natural intuition about hot and cold. But temperature is a rather derived quantity. It's a derived mathematical quantity that begins with the notion of entropy. Sorry, it begins with the notion of energy and the notions, twin notions of energy and entropy. And so let me tell you what temperature is. When a system is in thermal equilibrium, and we haven't defined that yet. If we get to it tonight, we'll do it. But it just means that a closed system has been allowed to evolve for a long enough time that it just settles down to some equilibrium configuration. And it may be that that system, it doesn't have to be a closed system. I take back closed system. And a system in contact with a lot of other environment. If the environment is not changing with time, the system under consideration will equilibrate in a certain sense that will become clear with its environment. Energy may flow from the system to the environment. In that case, we say the system is hotter than the environment, or the energy may flow the other way on the average. And in equilibrium, on the average, energy is flowing neither way. Okay? In thermal equilibrium, what characterizes the thermal equilibrium of a system, so here we have a system. That's our system. Consists of a lot of degrees of freedom in there. It may be interacting with an environment out here and exchanging energy with it until it comes to equilibrium. It has a collection of states. Let's label them by I. And each state I has an energy E sub I. Okay. E sub I, and so forth. Okay. Now, when a system comes to equilibrium, it doesn't come to a particular state I. It's interacting with its environment. Energy is going back and forth. Complicated things are happening. But on the average, in equilibrium, there are some probabilistic ideas, some probability, just probability, that the system is in the ith state with energy E sub I. That becomes probabilistic now because when it's interacting with an environment, well, you get the point. There's some P sub I, and that P sub I satisfies some rules. The first one is that the sum of all probabilities is 1. Another rule, it's not even a rule, it's a definition, is that if I take P of I, multiply it by the energy of the ith state, and sum over I, that's the average energy. I guess we can call it E. That's the average energy of the system. When you say average, what I really have in mind is that the energy is constantly changing. It fluctuates, some extra energy goes out into the environment, and then it comes back in, and so forth, and it's constantly fluctuating. But over short times, it averages, and this is the equation for the average energy. We have that. And finally, we have a notion of entropy, and the entropy is just this notion up here. Okay, now, what is the probability distribution P of I? What does it depend on? Well, first of all, among other things, mostly what it depends on is the average energy in the system. Now, the average energy may depend on the nature of the environment. If the environment is very hot, the average energy in here may be high. If the environment is cold, the average energy in here may be cold. But there's some average energy Here it is, average energy, and it can be different. Depending on the precise nature of what's going on, the average energy can be thought of as a parameter. You can change it. You know, you can change the average energy of a pot of water by putting it on a stove, or you can cool it down by putting it out in the snow. So you can change the average energy, and in that sense, the probability I depends on the average energy. Now, the way to think about this is for every value of the average, I'm not going to put complicated bars around this E. This now stands for average energy. At every given average energy in thermal equilibrium, there's a probability P sub I. Of course, if you increase the average energy, then you tilt the probability distribution toward larger energy values of E sub I. All right, so that means that there's not a single probability distribution that you call equilibrium. There's a family of them. There's a family of them for each value of E for this horizontal axis could either plot the ith state of the system or it could plot the energy of the ith state. But for each value of the average energy, there's some probability distribution. For every value of the energy, we can now put in here, let's put in here E. Let's put a comma in there. For every energy, the total probabilities have to add up to 1. And what about this equation here? On the right-hand side, this E here is just the average energy. It is just the average energy. So that defines the average energy. If you change the average energy, if you change the energy of the what's in the box, then the probability distribution shifts. Oh, I should draw it so that the area under it is always 1. The area under it, or the total probability, should always stay to be 1. So maybe like this. Which one corresponds to more average energy? The one which is peaked further out. I'm imagining the energy increases as we go in this direction, E of I. As we move to the right, energy increases. And so the probability distribution, which is peaked further to the right, I'm not doing this well. The area under each one of these should be the same, but there's a one-parameter family of equilibrium distributions like this, which we haven't calculated yet. We don't know what they are. But as a matter of experience, for each value of the average energy, there's a probability distribution, and that's called Pi of E. Every single one of them satisfies the sum rule here, and the average energy is equal to this quantity here. Yeah?
Things seem circular to me. The average energy depends on the probability distribution, but the probability distribution depends on the average energy. I mean, you didn't really put the E in that second equation with the I.
Which equation here?
Down the last equation, down
This
that
here?
one there. Put in PIE, like you did upstairs there. You put an E in there, right?
Ah, yes, thank you, good.
So, but that E is really bracket E, so it's like bracket E, you have to use bracket E to define bracket E.
Let's for the moment just say, from experience, there are a sequence or a one-parameter family of probability distributions. Okay? So here's a one-parameter family. The parameter is called E for the moment, but it doesn't have to be called E. Call anything you want. A family of different probability distributions. Each one of them has an average energy. All right? So once I know the average energy of it, I can think of it as the probability distribution for that given average energy. Right.
Do you have a quick question?
Yeah.
So is there a reason, if we assume a closed system, is there a reason that you say average energy instead of total energy?
Yes, because I'm imagining that the system, we're talking now about the system as opposed to the environment that it's in. And there's a constant interchange of energy back and forth between the system and the system. We'll call the system. The rest of it we'll just call the heat bath. Right? So it could be the atmosphere. It could be a box of gas with permeable walls that heat can leak through, sitting in room temperature in this room. Then it's constantly exchanging energy back and forth. The energy fluctuates. So the energy isn't definite. It has a probability distribution. If you go into the system at one instant and you measure the energy, you'll get one value. If you go in another instant, you'll get another value. And if you do many, many, many measurements, you'll get a probability distribution. Okay. Okay, is that clear?
Yeah.
Okay, good. All right.
One clarification here. You have these states I, and you have P of I, and E sub I. It's true then that there could be many, many states that have the same energy.
There could be, right? That's why I said, let's assume for the moment that there's a one-parameter family of them. That's correct, yeah, of course that's true. There are many probability distributions that you could write down that have the same average energy. Where we're getting this one-parameter family from will come later. We'll just say, as a matter of experience, if you know the average energy of the system, then there's some probability distribution associated with it. To give it a name, it's the Boltzmann distribution. But, or the Maxwell-Boltzmann, well, it's the Boltzmann distribution. All right, but for now, we're just doing a mathematical exercise, a one-parameter family of probability distributions parameterized by the average energy. No two of them have the same average energy by assumption. And the higher the energy is, of course, the broader the probability distribution is likely to be. And we'll take that as a given.
But there's an implicit assumption that each of the states are independent of the other ones. If you,
Each of which states?
The I state.
Oh, they're different, yeah.
So, but suppose the I state is correlated with the J state, then you have a,
What does it mean that the I state is correlated with the J
that
state?
whatever the energy is, the I state is the same
Say it
as the
again?
J state. Then,
Oh, you're asking what happens if there's more than one state with exactly the same energy?
no, that they're correlated, that the probability.
What does correlated mean? Correlated is a very technical term, and if you're going to try to transmit information back and forth between us, we have to do it with precision. So what does it mean to say that correlation is a very definite meaning, and it doesn't apply to this?
But it means that the probability, now I think about it, it's hard to describe, that
Good.
let me let it go.
Right. Okay.
I have a question.
You could ask, what if there's more than one state with exactly the same energy? Not average energy, but that there isn't that the E sub i's, E sub 7 and E sub 6 are exactly the same.
That's my question, yeah.
That's first of all, it never happens, and it's not particularly important. Degeneracy, that means equal energies for different states, is a very rare and unusual thing. We don't have to worry about it. Every state has its own energy. Every energy has its own state. Let's take that as a working assumption. Yes, question up there.
I think what's confusing me here is that I is the possible states of this
The
system.
microscopic description of the states, the precise, exact microscopic, every molecule, position and velocity, or whatever it takes to describe the exact microscopic state of the system.
Right. So if it's an arbitrary description, like, an arbitrary choice of what like I means, then it's hard to.
It's not
imagine-
arbitrary.
Like I'm saying, so state 1, we can label this state as.
Oh, how we label them. Yeah, how we label them. Okay, so good. So let's agree to label them in ascending order of the energy. Good. Right. Good. And let's take it as given that no two states have exactly the same energy, which is typically true except in very unusual situations. Okay, so then we have a clear notion of what we mean by I. We have a notion of what we mean by P of I, and P of I for different values of the average energy. The nature of this thing will become clear, not tonight. We don't have enough time tonight to work out the Boltzmann distribution, but we do have enough time to define the concept of temperature. All right. So consider the following. One more thing. Each one of these probability distributions, for each value of E, has its own entropy. Let's write it out. The entropy S becomes now a function of E. Now, it's not a universal function of E. It depends on these probability distributions. But given this one-parameter family of probability distributions, S of E is equal to minus the sum over I of P of I, comma E, log of, I don't need a bracket there, log of P. And so, for this reason, S becomes a function of energy, average energy in this case. The entropy, which is a feature of a given probability distribution, now becomes a function of the energy, because for each energy we have a different probability distribution. Okay? All right. So that tells us that there's a connection between entropy and energy if we know this one parameter family. And as I said, we'll discuss later where that comes from. Now let's ask a very funny question, an interesting question. How much energy does it take? Each one of these probability distributions, parameterized by a given average energy, the higher the average energy, the more they'll spread out to the right here, in particular to the right. We could ask, how much energy does it, how much do you have to change the average energy? How much do you have to change the average energy in order to change the entropy by 1 bit? 1 bit means log 2. Okay. How much do you have to shift the energy here in order that the entropy changes by 1 bit's worth? And the answer is going to be disappointing, because I'm just going to write a formula on the blackboard which is totally obvious. The answer is that the change in the entropy, how did I write it? Let me see how I wrote it. Yeah. Sorry. The change in the energy is going to be equal to the derivative of the entropy with respect to the energy. Sorry, derivative. The change in the energy. The change in the energy when I go from one probability distribution to the next will be equal to the derivative of the energy with respect to the entropy times the change in the entropy. This is an identity. I mean, this is assuming nothing more than that things are smooth functions that can be differentiated. The change in the energy in going from one probability distribution to the next is the derivative of the energy with respect to the entropy times the change in the entropy. It might have made a little more sense to you if I would have written it the alternate way. Then in going from one distribution to the next, the change in the entropy is equal to the change in the energy divided by dE by ds. Incidentally, there's no difference now between partial derivatives and total derivatives, just the derivative of E with respect to S. Okay. In some problems, there may be more variables, and we might have to keep track of more variables. Here, it's just derivative of E with respect to S times delta S. Or we can write it in this fashion here. This is trivial. There's nothing insightful here. It's just a definition of what I mean by differential changes. Question?
It seems that you're talking about the variation of the entropy with respect to energy. So energy would be
Yes.
the variable and S the function. Would it be not more logical to do ds dE instead of dE ds?
Either way, dE ds is the inverse of ds dE. Yeah. Yeah. This is also equal to ds by dE times delta E. All the same thing. Okay. If, for example, I want to know how much do I have to shift the probability distribution, how much do I have to shift the energy in order to change the entropy by 1 bit, then I would just stick in for delta S 1 bit, namely log 2. Right? So that would tell me how much energy it takes to change the entropy by 1 bit. Right? The main point here is this object over here. This object is called temperature. That's what temperature is. It's a derived quantity, and it tells you how much you have to change the entropy, or either way you say it, how much you have to change the energy in order to change the entropy by a certain amount. I sort of fixated on 1 bit, but it doesn't matter if it's 1 bit, as long as it's small. As long as it's small. Or using differential formulas, I don't know why I write delta, just D. The definition of temperature is such that dE equals T, temperature, times ds. And that's the only definition of temperature that's universal, general, and dE equals T ds. Sometimes written ds equals 1 over T times dE. Okay, one point that's interesting, well, it's a little bit interesting. If I change my units, from these physical units to human units, then this formula doesn't change. And the reason is, or it does change, of course, but it changes to become equals T measured in Kelvin times ds of the Carnot, and why? Because the Boltzmann constant cancels. Capital T is K Boltzmann times little t, and capital S, where is it? I seem to have lost it. No, here it is. Capital S is 1 over K Boltzmann times S Carnot. So they cancel, and this is why Carnot, who wrote this formula here, he wrote the energy equals little t ds. The K Boltzmanns, the Boltzmann factors cancel out of that. One gets a K in the numerator, one gets a K in the denominator. I'm just telling you this because you may wonder what happened to the K Boltzmann if you go read a book on standard thermodynamics and you say, wait a minute, what happened to the K Boltzmann? Well, they cancel out in the definitions. So here we are. Definition of temperature. It's an odd and an abstract definition of temperature, and it's not in the least bit clear from this what it has to do with temperature as you experience it. So I'm going to tell you what it has to do with temperature now. Yeah.
So we have that the entropy is a function of energy.
Yes.
And what you're sort of saying is
Yeah.
it's invertible. So is that obvious that it's invertible?
It's not obvious, but it's usually true.
Okay.
Yeah. There are counterexamples. There are counterexamples. And I would also say it is typical of normal physical systems that the entropy and the energy are monotonic. That when you increase the energy, you usually increase the width of the probability distribution, and in so doing, increase the entropy. We will take that as a given for now, that energy and entropy are monotonically increasing functions of each other, single valued, and we can come later and ask, is that always true? The answer is no, but when it's not true, unusual situations. Okay, so we're going to assume then that the energy is a monotonically increasing function of entropy, or entropy is a monotonically increasing function of energy, and that means the temperature is positive. dE by ds or ds by dE are positive. Assumption for the moment. And as I said, what it means is that when you increase the parameter E, you spread the distribution over a larger number of states. We're going, as I said, we're going to prove some of these things, most of them, but let's take it as given for now. Okay, so then the question is, in what way is this definition of temperature in any way related to the familiar concept of temperature? Now, what is the familiar concept? Oh, sure, ouch, I burned myself, but can we do something that's a little bit more physics-oriented? The basic fact, yes?
How about the color of the object as it heated up?
Well, okay, but that depends on the properties of light and so forth. That's true, but it's not really a statistical mechanical concept. I mean, we can have a box of gas without having light. So there's a statistical mechanics notion, but I'll tell you what, okay, you could think of 1,000 things that temperature has to do with, right? But the really useful definition, the definition that's closest to being general, is that temperature is a measure, or differences of temperature. If you have two systems, now let's take two systems. And let's, for simplicity now, suppose the two systems are isolated. This is system A and system B. And they're connected by a thin pipe. A thin pipe simply means that they can exchange energy with each other, but weakly. That little bits of energy can go back and forth between them and cause the energies to fluctuate, but on the average, each one has an energy. Now let's start them out without having been in contact. They start out not being in contact. They're each in equilibrium, but at a different temperature. At a different temperature. Let's call this one TA and TB. We know what temperature means. Temperature is the rate of change of energy with respect to entropy, an abstract definition to be sure. But each one of these boxes has been prepared with a given temperature by whatever it takes to make them have whatever temperature they have. And now connect them, and connecting them simply means allowing them to interact with each other and exchange energy back and forth. Okay? Which way does the energy flow? That's the most basic concept of temperature, or the most basic concept of temperature is that heat or energy will flow from the hotter, in other words, the system of higher temperature, to the system of lower temperature. And we can prove that. Arbitrarily, let's say that TB is bigger than TA. If it's the other way, then we just interchange A and B. Of course, it's possible that TA exactly equals TB, and we will see in that case that heat doesn't flow either way. Okay, on the average, or heat meaning energy now. Okay, so what we need to do, we need to write down a couple of simple, I left out one step. I left out, again, something which will not become completely clear till later. It's the second law of thermodynamics. The second law of thermodynamics, which I have given you no reason to believe at the moment, right? You can take it as a postulate for the moment, but we will do a lot better. The second law of thermodynamics says that when you allow the system to come to thermal equilibrium, when you allow A and B to equilibrate, for heat will flow one way or the other way, we don't know which, energy will flow, but eventually it will come to some sort of compromise equilibrium. The second law of thermodynamics says that the entropy increases. Okay? So let's try to follow the line of reasoning now. The total entropy of the system, S, is equal to the entropy of A plus the entropy of B. Why is entropy additive? Does anybody know? From the mathematics. Because it's the logarithm. Yeah, because it's the logarithm of something. Probabilities multiply. If you have two systems and each one has some sort of probabilistic description, the probability for the whole system to have some property multiplies. If you take the logarithm of probabilities, it adds. So entropy is additive. The entropy of the whole system is SA plus SB. Okay. Another fact, another useful fact. We're going to write down some useful facts. The second useful fact is that when the system equilibrates by exchanging energy, the total energy is conserved. All right? Here's the first law of thermodynamics. First law. If the energy of A increases, then the energy of B decreases by the same amount. So that says that dEA is equal to minus dEB. Or the change in energy, of A and B has to add up altogether to 0. I'm not sure we're going to make it through this. What time is it? Yeah, maybe we will. Okay. Next, the second law of thermodynamics. The change in SA plus the change in SB is greater than 0. Entropy increases. Again, something we will need to justify. Finally, for each one of these, the change in energy A is equal to the temperature of A times the change in the entropy of A, right? That's E, that's dE equals TdS, definition of temperature. Likewise, dEB is equal to TB times DSB. All right, hold on to these equations. Lock them in your head, because I think we are going to have to move across the hall.
For more, please visit us at stanford.edu.